last speaker for today. I hope not everyone is getting tired. It's actually local. TU Delft. Dr. DiCarlo from TU Delft will talk about initial steps towards closed-loop control of superconducting quantum circuits.
Great, thank you very much. Good afternoon, everyone, and thanks for sticking around for the last talk of the day. I'd like to thank the organizers for the opportunity to speak to you today about my group's current work towards realizing feedback control of superconducting circuits that we use for quantum information processing. I'm a bit new to the European circuit and also the only representative from TU Delft at this conference, so I'd like to spend a few minutes to provide a quick introduction, let's say. So I'm very excited to be starting a new group within the quantum transport section of the Department of Quantum Nanoscience in Delft. Delft is a lovely place, especially when the sun shines. Maybe not as pretty as Oxford, but still much prettier than Yale, where I used to be. I have the pleasure of working with four great colleagues within this quantum transport section. Quantum transport section, I have to say, I feel is a bit of an outdated name, because nowadays few of us in this section do quantum transport, whereas most of us focus on various approaches to realizing solid state quantum information processing platforms. So you see here in this summary slide a bit the diversity of our research, and I'm the young guy working on superconducting circuits, and next to me the four more senior staff work on other approaches. Lieven van der Sijpen pursues quantum information processing with spins and quantum dots, also does work in graphene. Leo Kouwenhoven now is very dedicated to the search of Majorana fermions in the solid state and the realization of Majorana fermion-based qubits. Ronald Hansen is a specialist in quantum information processing with electron and nuclear spins and diamond. And Val Spiller works on various approaches to making solid state single photon sources and detectors. We collaborate very strongly, and I'd like to give you here as an example a recent activity that combines the work of Ronald Hansen's group with mine. Presently we are trying to build an electron spin ensemble based memory for the superconducting quantum processor here, following very exciting initial developments at Yale and Saclay. Our particular interest is in realizing an architecture that is compatible with not so small magnetic fields. We're talking fields on the order of 300 milliteslas that would allow us to work with spin ensembles that do not have zero field splitting. In particular, we're very interested in working with ensembles of P1 centers in diamond, and our first step forward in this direction, as you can see here, is the observation of strong avoided crossings between an ensemble of P1 electron spins and a superconducting resonator at moderate magnetic fields. I won't have enough time to go further into this, but if you are interested in this kind of hybrid approach, please ask me further after the talk. Now, Ronald Hansen was initially very excited to come here due to a PhD defense in his own lab and teaching requirements he couldn't. And I told him, well, hey, don't worry too much. Give me a couple slides and I'll tell the guys at ONR about the very exciting stuff you're doing. Because it really is quite fantastic. I'd like to summarize it briefly for you. Ronald has a vision for realizing quantum networks with spins and diamonds. And in working towards this vision, he's having very neat intermediate results that I will summarize for you in a couple of slides. The vision is to work with basically little hubs with a few qubit registers each that communicate by means of single photons. And so at each hub you find an NV center in diamond, in this particular case, where an electron spin couples to various nuclear spins. And this electron spin, if you will, serves as a quantum bus, mediating the interactions between these guys. It also allows a form of readout because it is optically active, and so in a sense it's the starting point for the communication between various hubs in the network. In achieving this vision, he's been, with his group, developing a really remarkable quantum toolbox. He uses magnetic resonance techniques to do single and multi-qubit operations within each hub, and then does phenomenal single-shot readout, optical readout of the electron spin, and these optical transitions can be tuned in situ using electrostatic gating in his system. And now the next step forward is achieving spin photon coupling and realizing long distance coupling between distant hubs. So they have shown using dynamical decoupling beautiful control of single qubits from decoherence, and now extended the idea to a multi-qubit system, and they've realized a technique called decoupling while compute, by which they can do dynamical decoupling effects in a multi-qubit register, and meanwhile perform some useful computation. In their case, they realized a 2-qubit version of Grover's algorithm. Okay. Regarding the spin-photon interface, they've realized a beautiful projective single-shot readout of the electron spin in a few qubit register. And very recently, they made a step forward by demonstrating interferences between photons coming from various hubs, if you wish. So, once all of this is put together, they're trying to do beautiful demonstrations in a solid state of things like quantum teleportation and quantum error corrections and so on. Alright, so that was my brief summary of what my colleague Ronald Hansen does when he's not collaborating with me. And I'd like to show you that in my own line of work we're pursuing very similar goals, only in a different context, using, strictly speaking, only superconducting circuits that are strictly man-made, strictly man-designed, so to speak. So I'd like to tell you the story and where we are towards actually building feedback control in these systems, and why I think this is an important next step in our community. So the architecture I use for doing quantum information processing is known as circuit quantum electrodynamics. As the name implies, this is a solid-state analog, a quantum simulation, if you will, of cavity QED. This was pioneered by Andreas Waraff, who is going to talk tomorrow, as a postdoc at Yale. He basically realized the transformation from cavity to circuit QED, replacing the optical cavities with a microwave transmission line resonator. The mirrors you see are replaced by capacitive gaps into a coplanar waveguide structure, and the atoms are replaced by little circuits here we like to call nowadays transmon qubits. And the beauty of this, I think people didn't realize this from the very beginning, but gradually it became evident that this architecture really was a powerful platform for doing quantum information processing, not just simulating the things that cavity QED was having a hard time doing, like achieving strong coupling between atoms and light. And it really took off. Part of the beauty of circuit QED is the multiple functions that a resonator can perform. So in addition to protecting the qubits from the 50-ohm world that is all too happy to suck energy from these little circuits, it mediates the interaction between any number of qubits you might wish to put inside. So the capacitive couplings of each qubit to the transmission line resonator allows you to achieve an effective qubit-qubit coupling even between circuits that are separated over several millimeters. Okay, and a final and very critical use of of the resonator is providing a means for performing qubit readout, because as we'll see, the resonance frequency of the resonators will depend on the quantum state of all the qubits you've placed inside. So it allows you a means of performing joint qubit readout. My time as a postdoc, I was maybe the third generation postdoc working in this architecture, and I was very fortunate to participate in the development of quantum processors using this architecture. So a 2-qubit device we built in 2009 helped us prepare and detect entanglement between two quantum qubits, on a chip. And with this we realized, I guess at the time, a first for solid state quantum processing, simple versions really, rudimentary quantum algorithms, the 2-qubit Robersers and the Deutsch-Jones algorithms. We quickly upgraded from 2 to 4 qubits in 2010. We used this to generate and detect 3-qubit entanglement using exactly the same technology, if you will, to produce and detect the entanglement. And more recent developments include the realization of an efficient 3-qubit Toffoli gate, which we could put to use to realize a measurement-free version of the most rudimentary quantum error correction codes. That's the 3-qubit bit flip and phase flip codes. Circuit QED continues to grow, and the circuits are becoming more and more complex. An interesting recent development, I show you here an example from my lab in Delft, is to decouple the coupling and readout functionalities of resonators. So here's a device with 2 qubits. You see here, each one is coupling to 2 resonators, a central coupling bus, if you will, a high quality factor resonator that doesn't couple to the outside world. So we use this to mediate interactions between the 2 qubits. And alongside each qubit, there's a dedicated quarter wave resonator that we use to provide individual qubit readout. And so using frequency multiplexing, we have access through one port to individual readout of each qubit. And so I should say that this might be an example from my lab, but in reality, similar ideas are being explored worldwide by Yale, UCSB, ETH, etc. Now, I'd like to tell you a little bit more about how we control these circuits. How do we actually realize 1, 2 qubit? Yes, sir.
In optics, we have this problem of detection efficiency.
Yes.
So what is there an analog problem here, and what is the figure of merit you have for how efficiently you can read out the state of your qubit?
Oh, I'll be talking a lot more about that. Okay. If you bear with me a few slides, I will tell you about our efforts right now to achieve high fidelity readout and what metrics we use to quantify it. If you give me a few more minutes, I hope to. And if not, ask me later. Okay, so the first thing I want to tell you, if you're not familiar yet with these so-called transmon qubits, is that they themselves are like resonators. They are lumped element LC-like resonators, except the inductance L is made nonlinear through a Josephson junction. And so it's a multi-level system really, which can be made flux tunable by splitting that one Josephson junction into a pair of Josephson junctions and threading flux through the area between them. This allows us to make the inductor tunable, and in this way we can realize an effective 2-level system that we can tune over gigahertz frequencies on nanosecond timescales. But what's really important for what follows is that this is not a true 2-level system. There are higher levels in this anharmonic oscillator, and you will see how we start putting these additional levels to great use when doing computation. For our 2-qubit device, I show you here some spectroscopy which shows how using local flux control we can move qubits over gigahertz frequency without really bothering other qubits that there may be on the device. So here you see a large avoided crossing between a qubit and the one cavity in the system. This is the so-called vacuum Rabi splitting, which shows evidence here of the very strong coupling in the system. And then when this qubit comes into resonance with the other, you see here another apolytic crossing, which is that qubit-qubit interaction mediated through the cavity. And so this is known as the swap interaction because exciting one qubit and then pulsing right into the zone will induce a coherent exchange of that single excitation between the two qubits. How do we do single qubit operations in the system? Well, you won't be surprised to hear we do the analog of shining a microwave laser on the transition. And so that's simple. You just get a commercial signal generator and you have to do some clever pulse shaping. It's not very hard. Our pulses take on the order of 10 or so nanoseconds. And we can control where we induce rotations about in the Bloch sphere by controlling the phase of that microwave tone. And so this stuff works very well already at the level of 99% a couple of years ago. Now we take pleasure in saying we've got an extra 9 in fidelity. So we're approaching the performance, I think, of ion traps gradually. And so, yeah. And I should mention that these fidelities tend to be relaxation time limited. So as the coherence goes up, this number will continue to increase. Alright, so that's how we do single qubit gates. How do we do 2 qubit gates? Well, we use flux pulsing on nanosecond scales to bring qubits into resonance with each other. Now, you'd be surprised to hear that we don't actually use this interaction, we sort of stop short of it. And you may wonder why. And the reason is that that's not evident here in this picture of single excitations of the system. What's really happening, which is very exciting, in the 2 excitation manifold, is that the computational level 1,1 runs into a non-computational level, 0,2. Remember I said the transmon is a multi-level system. And so when this happens, if you adiabatically follow 1,1, you see the frequency of 1,1 no longer matches the sum of frequencies of 0, 1, and 1, 0. So a flux pulse might look something like this. You adiabatically enter the avoided crossing, you stay there, and eventually you come out. Now what's nice is when you go through this adiabatic excursion, each of these computational states acquires a quantum phase. And the quantum phase acquired by each depends on the details of your excursion. But what's really nice when you're in the interaction zone is that the rate at which 1,1 acquires phase no longer equals the rate at which these 2 acquire phase. And so by clever shaping and timing of this pulse, I spare you the details here because they're really technical and not essential for this talk. You can generalize, you can make any phase gate that you wish in the system. But in particular, the one we care about is one where one and only one of the 4 computational states acquires a -1 in the style of the traditional conditional phase gate. And once you've got that and the single qubit gates, you can start putting little quantum programs together and begin having some fun with algorithms. So here's a simple circuit using a single 2 qubit gate that realizes a Bell state. Here I show you experimental tomography of the system, of the state produced here. And if you just change which of those 4 guys gets the -1, you can make any of the 4 standard Bell states. And this all works with 90-something% fidelity. So concurrence in the 90% as well. Great. But how do you detect entanglement in the system? Well, to perform tomography, as the theorists in the room know perfectly, you need to know the expectation value of all 2 qubit operators in the system. Oh, 2 qubit poly operators in the system. We experimentalists call this the poly set, and we like to decompose it into single qubit terms, which we call the Bloch vectors, and correlation terms. So for a 2 qubit system, you need to have measured the expectation value of these 9 correlations. Great. And so how do we do that? When we have a single channel measurement in the system, we don't have access to individual readouts. So how can you get access to all this information using this single channel? Well, the neat idea is that in circuit QED, particularly in the strong dispersive regime, the shift of the cavity that depends on the qubit state can be very large compared to the lining. So by probing the transmission at one of these frequencies, you're asking the cavities questions like, are all the qubits in the ground state? And the cavity gives you a 1-bit answer, yes or no, depending on whether transmission is high or low. And so when you look at the measurement operator, which is essentially a projection on the 2-qubit ground state here, you see, and you expand it in terms of the Pauli operators, you see that this readout gives you beautifully access to single qubit terms and those crucial 2-qubit terms you need to do full tomography. So the way you get a tomograph is by essentially asking 15 different types of questions by pre-rotating using single qubit gates before you turn on the measurement. In this way you will change z's into x's or minus z's, or depending on the nature of the question. So you ask 15 different questions, invert a matrix, and voila, you get the 15 expectation or ensemble averages of the 2-qubit Pauli operators you need. So here I show you examples of tomography of 2 qubits, and you see clearly that the sharp distinction arising in the Pauli set between non-entangled and entangled states. You see here a shifting of strong correlations from the block vectors, strong bars from the block vectors into the correlation space. So here's if you see this, you just say, aha, this is a very highly entangled state. Now for us who believe in quantum mechanics, that's perfect. That's a smoking gun proof we've got entanglement in the system. We're not so much concerned with fundamental questions like, is this really quantum? We'll prove it's quantum by doing an algorithm that's useful someday. But if you are a skeptic, you'd want to see something like a violation of Bell inequality. And I'm afraid I can't appease you entirely because this system is subject to tons of loopholes, which we'll never get rid of. But at least I can entertain the possibility of a Bell inequality violation by doing a movie, basically, by rotating one guy before measurement, in analogy to rotating the polarizer in a typical optical experiment. And so here you see a movie, so to speak, of how the single qubit terms, which are ideally 0 and are very much so over the entire range, and also the evolution of the correlation terms. And you can see for particular choices of this pre-rotation angle, we amply violate the CHSH type inequality. So we don't quite get to the 2.82 predicted, the Searleson bound, but we understand the deviations to be consistent with relaxation in the system. And so we step outside the classical bound quite comfortably. Now, if you believe quantum mechanics, you can use the CHSH as an entanglement witness, actually. You can easily show that if you exceed square root of 2 in the absolute value of a CHSH operator, you have a certificate of entanglement in the system. So it's one way of doing entanglement witnessing, which is an easier bound to break than the LHB. All right, so with this system, we've done quantum algorithms, particularly the 2-qubit Grover search. I'm afraid everyone in this audience knows what this algorithm does, so I will try and speed up here. The essence is to find, if you wish in mathematical terms, that special input to a function for which the function returns 1. You can think of it as a simple search problem, and a way to motivate it would be an example like this, where I give you 4 cards face down and I tell you that one of them is a queen, and I ask you, without giving you any further information, to pick the queen for me, find the queen for me. Classically, you'd have to unveil on average 2 1/4 cards to get to the right answer. And the beauty of this toy algorithm we know as Grover's algorithm is that for a game like this with 4 cards, you get the answer in one go. And so here's a little movie, not a Hollywood movie, but a Quantum Geeks movie, of how our little processor can be programmed, and how it uses at each step of the algorithm entanglement and disentanglement to get at the answer. So in this particular example, the secret answer was 1, 0, and you can see here at this point in the algorithm how the answer is being tagged in a quantum phase here. If you're familiar with density matrices, you will clearly recognize that this uniform superposition has had the sign associated with the answer flipped. And this is a maximally entangled state, which then the analysis part of Grover's algorithm disentangles to produce one of the 4 computational states, which can then be faithfully measured. This worked with 80-something% fidelity. One serious limitation of our approach was that because we have joint readout, actually, we are precluded from demonstrating a quantum speedup. And so this took a while longer, and our friends in Saclay, using individual qubit readouts, have now claimed, the first realization of a quantum speedup with a superconducting circuit. Great. So the promise of superconducting circuits is scalability. And how much more time? Just 15? Oh my gosh. Okay, I'm going to hurry up now. Well, I'd like to show you that these systems scale using the same type of C-phase gates and detection mechanisms. You can basically expand to 3 qubits very easily. And so we have now extended the generation of entanglement onto 3 qubits. And here I show you the polyset corresponding to a GHZ state. If you're familiar with this very famous state in the history of quantum information, you will recognize here the 4 bars, the 4 correlations that made the GHZ interesting initially. If you are into quantum error correction, you will recognize the 3 bars that make the GHZ state interesting for error correction, namely the signatures of the GHZ class states as eigenstates of 2-qubit parity. Wow, so because I'm starting to run out of time and I haven't actually even gotten to the stuff I'm doing in Delft, I'm going to speed this up. Like with the 3 qubits, we were basically able to do the analog of a CHSH inequality violation in the form of a Mermin inequality, which was amply exceeded above the LHB and by several bounds of 2. So there's proof of 3-qubit entanglement in the system. And now we can use this 3-qubit system in analogy to what we did with the 2-qubit system to perform that famous toy algorithm you'd want to do once you have 3 qubits. And that's measurement-free, that's 3-qubit error correction. The idea of this simple code is to encode a single qubit state in a GHZ state of 3 qubits and to protect it against the possibility of single flips induced by an environment on either of the qubits. Now, this type of algorithm, which includes measurement and feedback, you see, is not something we have at our disposal right now. And there's a clever trick, which is known as measurement-free error correction, which replaces the parity measurements that are key in the diagnosis of errors and the subsequent conditional actions you do in the system with a single gate, quantum gate, known as the Toffoli gate. We have achieved this Toffoli gate in analogy to the 2-qubit gate. The idea, I'll just get to the gist of it, is to find somewhere in the spaghetti of multi-levels in the system a configuration by which the computational state 111 enters an interaction with some other level that doesn't happen anywhere in one of the lower manifolds. So ideally, you want to have an interaction between something like 111 and 003. But that avoided crossing in circuit QED is very small. So the idea is to play a little trick, is to use another avoided crossing to convert 111 to 201, and then to have that 201 level run into 003. And that is the essence that lets you acquire a 3-qubit phase in the system to realize that all-important Toffoli sign gate. So it works very well. Here we show you how you can classically, characterize the action of this gate. This is the classical truth table. The fidelity is about 86%. We've done quantum state tomography and get a fidelity close to 80%. Now, once you have this gate, you want to put it all together and demonstrate one round at least of phase flip or bit flip error correction. And the algorithm works quite well. You can see here that when you introduce errors purposely into the system and you perform error correction, instead of your single qubit fidelities decreasing linearly with this probability, you see that the linear terms are suppressed, and now that the degradation is only quadratically dependent on the induced error probability. So there's some parameter of probabilities where you can clearly see that error correction is doing something. Okay, sorry I had to run fast to recover some time, because I want to tell you about where I'm going now in Delft with my group and where I want to be 3 or 4 years from now. Everything I've told you so far, as from my perspective, is just open loop control. See, the paradigm so far has been like this. You tune up something, you execute it, then you perform a very heavily averaged measurement, partly to average out quantum noise in readout, but also, in our case, traditionally, a lot of unnecessary technical classical noise added by readout, to obtain a tomograph. And then you or your student, whoever's on the project, is going to look at what came out, wonder what went wrong, reprogram the thing, and basically complete the loop. So you could say that this is a human-assisted feedback, and that's what we're always doing in the lab. But yes, this kind of, let's call it tune-up, bring-up of our quantum systems is really important, and we're all working to realize classical feedback loops that perhaps someday involve us less and less. Because as we work with higher and higher number of qubits, well, you want all of these things to be happening automatically while you prepare for the fun stuff. But this is not the kind of closed-loop control that I'm particularly interested in at the moment. I'm interested in quantum feedback control. The idea of measuring a register or a subset of a register of qubits, deciding on the fly something, and conditioning on that classical decision, acting back on the system. This is known as feed-forward or feedback, and theorists I noticed earlier this week take this for granted. You just, things like one-way quantum computing or teleportation-based quantum computing, this stuff is taken for granted. The reality is that it's super difficult, and we're not there. Why? It's because our readouts are really quite not very good yet. The best readout I worked with before my assistant professorship had a fidelity of about 10%. It didn't matter because tomography was all I was doing with it, and I could afford to average. Another problem is that the feedback needs to happen on timescales that are fast compared to the qubit coherence times. Until recently, this time in superconducting circuits was about 1 microsecond. And if you look at state-of-the-art electronics, you might be able to do a feedback loop with a latency of about 100 nanoseconds. But that's not an ample margin to work with. And so what we're working with now, luckily, is a new version of quantum electrodynamics, circuit quantum electrodynamics, where the coherence times are at least a factor of 10 longer. This is a beautiful development from the Yale group, which has essentially taken a step backwards towards cavity QED. We've replaced the transmission line resonators with actual 3D resonators. The beauty of this is that it stores, in this way you store the electromagnetic energy in vacuum rather than in lossy surfaces. And in this way, this simple modification, we've attained really remarkable improvements in qubit T1 and T2. Like this data from my lab, it's definitely the best data from my lab so far. It's not representative of the average, but we've achieved T1 times now of 85 microseconds, which is more than a factor of 40 better than the best stuff I got to work with. I should mention, we're doing this as well, but we did not pioneer this. We quickly adopted this breakthrough, I should say. Using dynamical decoupling, we came almost close to adding an extra zero to to the coherence time, but we're still working on that. So with these extra margins now, feedback is starting to look possible. Well, provided you can solve the readout problem. I'd like to illustrate the readout problem for you now. Traditionally, you measure transmission to the resonator, which you excite at the few photon level, and then you take whatever goes through the cavity and you try to amplify it with a semiconducting amplifier. When you do that, you see here, you do get a difference between the signals for qubit up and down when you average heavily. But if you look at single shots, you basically get two lollipops that basically overlap with each other almost perfectly. What we've done now is we've added a superconducting amplifier to the readout chain before the HEMT, and it really boosts the discrimination capability for single shots. How does it work? It's a beautiful, beautiful little system. What it does is you feed it a very strong pump, much, much stronger than anything that will come from the experiment. Think of this as my arm, the pump. And you add a little tone that comes from your experiment. And the characteristic feature of the parametric amplifier is that the reflection phase is very sensitive to the net power in the signal. So that if I add a little guy, say a nail's worth, to my pump, all of a sudden I can get a 45-degree shift up. And if I subtract the nail's worth of the pump, I will get a minus 45-degree shift of the whole thing. And so here you can see clearly the improvement in the discrimination capability of the readout. So when we did this, we were very excited. We said, okay, let's see what histograms we get when you do 0 or when you prepare 0 or 1. And much to our surprise, we got really nice separate histograms, but really annoyingly, we found that each histogram had kind of a doubly peaked structure. And after scratching our heads about what could be happening here, we concluded that maybe our qubits were not actually fully polarized. You know, we like to think they are because they operate at gigahertz frequencies at 50 millikelvin, so you expect perfect polarization into the ground state. But maybe not. So to test this idea, what we did is we performed an initial measurement, and then we post-selectioned on the single shot we got from this initial measurement M0, and then only kept the cases where we declared the first measurement to be high. So by doing this type of post-selection, or some people will call it heralding, we observed right away that the double humps essentially disappeared, convincing us that yes, indeed, although we don't understand the origin, we've got some residual qubit excitation. And so here, I'm going to show you how we put this to the test. Here's a Rabi oscillation that we obtain by controlling the initial rotation angle prior to measurement, without and with this initialization step. When we do not initialize, we have a contrast of about 86%. And when we do initialize, this contrast goes up to 97%. I was very, very excited when I saw this, because it showed us that for the first time, we have a readout that gets close to what ion trappers can do. It's also QED, actually. So you can measure the correlation of, if I do subsequent measurements, what is the probability I'll get the same answer on the second measurement. And so you can see that when this initial measurement projects onto the ground state, your chances of measuring high on the second readout are virtually unity. The opposite is not exactly true when you project into the excited state, but we understand that that is limited essentially by relaxation in the system. Basically, the couple of microseconds of time between having made a measurement and acting back on the system. So we have to make this as short as possible, the time between the measurement and the action, if we want to do better. But despite that slight imperfection, we can now play at making our own type of initialization gadget. So it's our very first feedback implementation. it's very simple. I'm sure it looks trivial to everyone in the audience. But let me reassure you, technically there's a bit involved in doing this. The idea is you project the qubit, you decide, well, did I project into the groundly excited state? And then to act back to apply a pi pulse or not, so that indeed deterministically you can prepare the ground state. We call these sequences make 0 and make 1. And I'd like to show you our first attempt at transforming this initialization from probabilistic to deterministic. So what we've done here is following an initialization step so that we know we start from, we know where we start from. We'll do a Rabi oscillation and then we will perform a measurement and, well, first we're going to characterize actually our Rabi oscillations and say, okay, what's the probability that after rotating by theta I will be in the ground state? And you can see here a unit visibility oscillation. Now, what happens when I do make 0 or make 1? So here we are going to ask, okay, after I do this procedure, what is the probability that I will have prepared the 0 or 1 as a function of the initial Rabi angle? And to be sure, ideally, this red curve would be 1 and this blue curve would be 0. But in this first attempt, basically we see that make 0 works at the 90% level, and so does make 1 after you basically average overall angle. So you can say the fidelity of deterministic preparation is about 90%. We have done our checks by changing the threshold for the measurement. We can see that indeed the fidelity, the average fidelity decreases as you move away from the optimal point as it should. Sorry. Okay, where is this going? Our current experiment is to use this technique to realize entanglement by measurement. So there's a simple way to transform a single cavity in circuit QED into a parity meter. So what you want is to arrange a situation where the resonance frequency for 1, 0 and 0, 1 are exactly the same, and that there's night and day between these resonances and the cavity resonances for 0, 0 and 1, 1. So you turn on a pulse at this frequency, and if you get transmission high, you will project ideally into the odd subspace. And if you get 0 transmission ideally, you will project onto the even subspace. So the plan is to basically realize this parity measurement, and then to first show its probabilistic functioning by performing tomography on the system conditioned on having measured low or high transmission. And then the next step will be to use feedback to deterministically produce the same Bell state that you want every time. And so that's where we're going, and I hope to be able to show you guys what happened with this experiment. So, by way of summary, I've shown you what I hope you see as a lot of progress in open loop control of superconducting circuits at the 2 and 3 qubit level. And now a new trend, which is to start putting in high fidelity readouts and measurement based feedback and feed forward into these little circuits. So I'd like to thank my extended family at Yale, where I was a postdoc, and my young new lab. If you know people who like this kind of stuff, are very technically minded, while also calling themselves physicists, please send them my way. We're looking for people exactly like that. And I'd like to thank our collaborators, particularly Conrad Leonard on parametric amplification, Ronald on our hybrid work, and also Tim Clapbike's group, with which we collaborate on disordered superconductors. And finally, thank you for your attention.
Thank you very much for this inspiring talk about superconducting qubits. There were some questions already. Are there more questions?
As with all qubits through your circuits, how does the entangling operation scale? Like you're using these transitions coming together. You can add more qubits
you ask me the question of, let's say I want to do a 4-qubit thoughtfully signed or 5-qubit, how will the numbers progress? I don't really know the answer to that. The question is not simple to answer because there are so many levels that you have to be wary of. If you have strong avoided crossings, you have to be very careful about how you either cross them or use them. And I don't have an answer for you on this specifically. I can tell you that the initial 2-qubit gate was 30 nanoseconds, and the 3-qubit version was 65. But I haven't looked into what it would take for 4.
Further questions? Guess everyone is already a bit tired. Thanks a lot for the talk.